All right, so hopefully everybody was working on this while I was working on it, and hopefully everybody's table looks similar to what I've got here. So take a look at it and check, make sure I didn't make any kind of mistakes like that, or if you've got something different, just let me know. Oh, excuse me. So at this point, now we're ready to sum this column together. So we want to sum all these values together. So we just want to add them all up. So in this case, we're looking at 2.176. Let me throw some of my calculator here. So 2.176 plus 0.884 plus 0.371 plus 0.679 plus 0.376 plus 0.552 plus 1.572 plus 0.307. All right, so it looks like I got 6.917. Oops, wrong pen. And then we want to multiply this by 1 over n minus 1. So since n was 8, n minus 1 is going to be 7. So we want to multiply this by 1 over 7. So times 1 divided by 7, which gives us 0.988 and a bunch of other stuff. So our R value in this case is 0.988. So that's actually really, really good in this case. So we'll see in a second like what good R values are and bad R values and stuff like that. And so the reason these guys were both negative, like these two columns, is kind of because this is going to be a positive direction slope. If your slope was a negative direction, these would probably be opposite. One would be positive and one would be negative in that case. Because with a negative direction slope, we'll end up with a negative R value. All right, so at this point, kind of pause the video. You guys work on practice 1 and practice 2. So in this case, you're doing everything, plotting the scatter plot. So do your best. I know you won't be able to get it perfect because these numbers don't necessarily line up exactly with the graph, but that's okay. Just do your best on it. Go through, figure out the R value to see what kind of a correlation coefficient you get for practice 2. And then when you're done, come on back and then we'll talk about the different properties of the correlation coefficient. All right, so at this point, hopefully everybody was able to calculate their R values and stuff like that. But now we need to know, well, what does that actually mean? What's a strong correlation? What's a weak correlation? Things like that. So first off, the main thing to notice with the correlation coefficient is it's always going to be a number between -1 and 1. So 1 being the best, which basically means it's perfect correlation, and so the dots actually land on a line. Like the scatter plot actually forms a line in that case. And the 1 means it's going to be a positive slope. So it doesn't say that the slope is 1, it just means that it's going to be a positive slope. Same thing, -1 means that it would be a negative slope and all the points are exactly on the line. So anything close to that, so like usually when we're talking about a strong correlation, we're looking for an R value that's like 0.9 or bigger or -0.9 and smaller. So that doesn't mean the other ones won't make a linear equation. That just means that it's really, really strong if you get an R value of 0.9 or bigger or 0.9 or smaller. And so again, just like I mentioned before, if R is positive, the direction of the scatter plot is going to be positive. If R is negative, the direction of the scatter plot is going to be negative. The closer to -1 and 1 we are, the better, the stronger the relationship. So if R equals 0, or if we're even close to 0, then that means there's no real association whatsoever. So again, the value of R is not connected to the value of the slope, other than it just tells us it's positive or negative. It doesn't tell you it's the actual slope. And the correlation coefficient, as you can imagine, since we're using every value in the calculation, because we're calculating the mean, not the median, excuse me, it is sensitive to outliers. So outliers could actually mess up the R coefficient in this case, the correlation coefficient. All right. So last thing, this is just kind of fun. So what you have to be careful of is because correlation doesn't necessarily implies causation. So what's that mean? So just because two variables are highly correlated, which means that they'll make a nice linear regression, doesn't mean that one causes the other. And so in this case, like the example of the house size and their price, this is what's called a causal link because you can't assume that in every case where there's there's a strong correlation. So because for example, there's a lot of other factors that go into a home other than just the square footage. I mean, because you could have a house, two houses that are 3,500 square foot, but one sits on a quarter of acre of land and one sits on 100 acres of land. So obviously, the amount of land is going to go into the cost of the amount of the house price as well. Like one house could have a pool, another house could not have a pool. One could have like a fancy, super fancy like industrial kitchen, and the other one could have like a microwave and a small like apartment fridge or so. So there's a lot of other factors that go into it than just that. So, but for example, there's one guy that's kind of going off the rails, and he has this whole book about how things are kind of related that actually aren't related. So I put the website on there if you wanted to go and look around because some of them are kind of funny. So like this is one of them that I stole off the website. So basically, the input variable is the consumption of mozzarella cheese, and correlates with the number of civil engineering doctorates that are awarded. So basically, if this was true, that causation was true, basically the more mozzarella cheese you would eat, the more likely it would be that you would get a doctorate in civil engineering, which we know isn't necessarily true. So even though these two things are correlated, it doesn't mean that they're one causes the other or anything like that. So it's just kind of a funny thing. So again, if you've got some time and you need a little break from doing math or anything, go check out this website because there's some funny stuff on there. But all right, so with that in mind, pause or stop the video, come on back, and we'll go to 12.3.